Thank you for coming to the Arthur Sweeny lecture, the 40th one. That it was supposed to be in 2020. Yes, unfortunately, pandemic wanted something different with us, and we are here in 2025 trying to catch the lost time. Yes, we are not in Proust. Yes, we are in the normal times. So, who is basically this year we'll have Professor Brus here, Nobel Prize laureate of in 2023 for chemistry, and he will talk about nanoscience in chemistry. But before that, I would like to talk about Professor Sweeny for a little bit, especially for young generation who might not know who is Professor Sweeny. Professor Sweeny was a beloved professor which was hired by Hunter College in 1930. In 1968, when Lehman became Lehman, basically he decided to stay in the Bronx. Okay, he was living in Westchester, yes. And he was the first marshal, yes, here, of the first commencement at Lehman College. So this is Professor Sweeny, a little bit like Dracula like me, bloody professor, yes. Yes, so you can say that it's coming from an old movie, yes. A very interesting character, beloved by his students. In 1968, when Lehman became independent, he stayed till 1974 when he retired. And his students, around 79 or 78, I don't have the dates clear yet, it was 78 or 79, maybe some of his students. Do we have some of Professor Sweeny students here? It's anybody here? Yeah, Professor Sweeny? It's any one of his students here? Unfortunately, not this year. Yes, so in 1978 or 79, his students pursued the first president of Lehman College to create this Sweeny lecture. The Sweeny lecture was not memorial because he was alive and he was coming until he was 94 years old and he died. And he was here, it's exactly in the room from where we're coming, yes, with Professor Lazarus and Professor Baumgarten, which was chair for 18 years of the Department of Chemistry. And basically when it became memorial, we start to change the format. So let me tell you to give you some updates. I will not repeat exactly what it's in my newsletter, everybody receive it. I would like to bring you some news about the college. You know that we have a new national recognition. Basically, we have Carnegie Foundation defines the research colleges in a different way, and Lehman was recognized with this year as a college, research college and university, RCU. First one is R1, R2, and now it's RCU for us, which is basically giving us a bump, but we are looking for R2, yes, in the next 3 years. So we have 80 undergraduate majors, over 60 graduate programs, and even 2 doctoral degrees we offer over 6 schools. We are basically the 4th best value college in New York, the 4th top performer in social mobility. We are the best university in North, number 5. We are bang for your tuition back in top 25. We are military friendly. We are best college in New York rank. We are the top public university in New York. We are of top 20 of social mobility of schools in 2024, best service of Hispanic service institution number 6, 12 public university in North for 2025. That is an increasing from previous year. Top 1 in a college in New York for health education. most diverse college, number 1, the top online college in New York, and the top online master program health education. So we are doing pretty well, and we are trying to do even better. I hope next year to come with new data for you. And I want to bring you some news about administration. Yes, you met the provost and the president earlier. I don't think that any one of them are here. We have a new president in the last 5 years, yes? That is an old news, 2021. Dr. Fernando Delgado, the president of Lehman College. Unfortunately, he's not here, no? And we have the new provost, starting with 2023, Jorge Silva Puras, who was also present today earlier. News about faculty, Professor Lazarus decided to retire in January 20. We had the celebration for him. And Professor Mills, Dean Mills, will step down from the dean office, and eventually she will retire, but we don't know when. We hope that she will stay. And I want to bring you news about faculty. Professor De La Parra here was hired basically starting with 2019. She established a cancer research group in the new science building. She's extremely successful. I will talk about her success a little bit later. Then is Dr. Patricia Gonzalez, which is a doctoral lecturer here in front. So 2021, correct? 2022. I had a debate with myself, but okay, I'll give you one more year, yes? No problem. She's a doctoral lecturer, and even if research is not required for her, she's very active in student education and chemical education, and also very active with the club. The club basically has to recognize, look, the club is here, helping. Dr. Yume E here, yes, she is an environmental chemist, environmental scientist. She just finished keeping her lab. She's launched her research at Lehman. So she's trying to purify our water, yes? So after she will purify our water, basically we'll have a better quality water. And not the last, Dr. Chuni Wang. Where it is? There he is. Come to us in fall 24, basically brand new, fresh. He is working in artificial intelligence. Don't take it the wrong way, guys. Yeah, so basically he's working in artificial intelligence, machine learning, on polymers. Am I right? Yes. So on soft materials. So, hey, move. Yes. Okay. Professor Kurtzman became full professor a while ago, and he received basically Maximum Investigation Research Award, MIRA R35 grant for NIH. Then we have Professor Derry. Oh God, yes, it's an associate, sorry. I will change it. I told you, I'm also an assistant professor, yes? I'm sorry. Receive an increasing access to radio isotopes by advancing radiochemical training capability grant from US Department of Energy, isotopes programs. Professor De La Parra, as I say, established her research lab in cancer treatment. She got a Felix Gross Award for outstanding research across the CUNY in 2022. 2 grants from NIH, and thanks God, this one, the Shore, was refinanced a few weeks ago, so we are good, yes? Columba. Professor McGregor and Benjamin McGregor and Barton Pye, they are working on radiochemistry, as you know, and they are very successful with grants, getting ion dynamic radioactivity, environments, and materials. iDREAM grant from Department of Energy. The Renew grant also for Department of Energy Basic Energy Science. And Ben, Professor Barton Pye, have a National Nuclear Security Agency grant consortium for nuclear forensics. It's part of 10 million a grant of $10 million. So pretty successful in terms of money. Let's say about that we are most proud about our students. And we have this year 19 potential alums, 17 doctoral students are now in the labs, and I signed at least 5 mentor forms for another 5 doctoral students which are coming. So in the fall, we are getting close to 20-something students. 6 undergraduate students were participated in research and got authors in the last year. And 2 of our graduate students, undergrads are going to the medical school, to the PhD programs. Nidhi Nobel will go to Stony Brook. Where is Nidhi? There. And Andrea Menendez was accepted at UMass Amherst. Hey! Okay. So, but the undergrads which are still here are doing things. Yes? Blessing Mukandov, basically from, she is here. Yes? Yes? She will go do an RU during the summer with Memorial Sloan Kettering and University of Iowa. She's working with Dr. De La Parra. Jonathan Colon, he's not here, no? It's basically working with Dr. Naftali O'Connor. We'll do an RNA RU at University of Albany, and Rebecca Abraham will do an RU with Bjorn Thompson Institute at Cornell University. Very proud of these future scientists. Yes, I hope that you are also. And now, I am moving farther, or not farther, toward the lecture from today. Yes, I don't want to bother me too much. You have to hear Professor Louis Brus, which is basically a Samuel Lehman Michael Professor of Chemistry at Columbia University, fellow of American Academy of Arts and Science from '98, member of the United States National Academy of Science from 2004, member of Norwegian Academy of Science and Letters. And he received basically the Nobel Prize in 2023. But before that, it also received the Distinguished Alumni Award from Association of Rice University Alumni. It's a co-recipient of Wood Prize for Optical Society of America, and it's also inaugural Cavalli Prize awardee for Nanoscience together with Sunio Ishima in 2008. And in 2009, he received a Wilbur Gibbs Award. And in 2010, he was receiving a National Academy of Science Award in Chemical Science. And 2012, he receives a Franklin Institute Bauer Award and Prize for Achievement in Science, as well as selected a Clara Vita Citation Laureate of Chemistry for discovering colloidal semiconductor nanocrystals. And as I say, basically in 2023, after a long work in nanocrystal quantum dots, he receives a Nobel Prize together with 1/3, each one of these got 1/3 of basically Louis Brus, 1/3, Mangonji Bhagwandi, another one, and Alexei Yakimov, another 1/3. So basically they share this award. Without any further ado, yes, I would like to invite Professor Louis Brus to give the speech for which you come. I hope that you didn't come for me.
Well, first, let me do a sound check. Everyone in the back hear my voice? My voice is weak, but you can hear me okay? Yeah. Well, you can see that I'm not well. The last 2 years I've been at home mostly, and but feeling better now and able to get out a little bit. I'm very happy to be here today to talk to all of you about our common problems. This lecture that I'm about to give is the same one that I gave, roughly the same one that I gave 2 years ago in Sweden. So here's a slide which attempts to compare nanoscience as it exists in biology. I'm looking for as it exists in biology with nanoscience as it exists in mankind, laboratory research. And this is mostly inorganic nanoscience related to electronics, moving electrons from one place to another. And there should actually be a third column, which is nanoscience in medicine, which I'm not really an expert on, but it exists. So you can see, starting from the macroscopic here, all the way down to 10 angstroms here, or 1 nanometer, this evolution, an ant. And it decides right in here, red blood cells. And here is ATP synthase. The protein on the top here is maybe 100 angstroms across. That's maybe twice the size of the nanoparticles I'm going to be talking about. DNA, maybe 10 angstroms across. And here are things made by men and women. Wheels in a watch. And going all the way down here is, you can see this is a carbon nanotube. I'll say a little bit more about that later on. There's 2 of them here, one going from here to here, and another one from here to here. These are pieces of gold on the surface that are electrical contacts. So this carbon nanotube can carry electrons under certain conditions, and you measure its current by putting electrodes on the end like this. Apply a voltage, current will flow down the wire, basically, as if it were a wire metal. Here is Smalley's buckyball, discovered, I don't know, maybe 10, 20 years ago. And here's a very fanciful picture of a nanocrystal of the type I'm going to be talking today, connected through ligands up to a scaffolding to DNA with some side groups on it. And the idea here is that you excite this nanocrystal with a photon. It creates both an electron and a hole on the inside at the same time. So the excited electronic state is neutral, but in the language of solid state, you can think of it as an electron combined with a hole, a positive and negative charge. So this work was not done in a university, and it was not done with federal funding. In fact, it was done entirely with private funding in a monopoly. AT&T, when I was young, is a national telephone monopoly. AT&T owned the telephone in your house at that time. And you paid your telephone bill every month, and a small fraction of that telephone bill, I don't know what small fraction, but maybe $1 out of 10,000 or something like that, went to the research area of the telephone company, Bell Laboratories. And so what the Bell Laboratories was doing long range and also short range, but also long range basic research in areas that would improve communications and improve computers, very primitive computers at that time. Material science, physics, mathematics, things of that sort. And you see it was a tremendous operation here. This is where I worked in this building for 20 some odd years. My lab was right over here. And I don't know, maybe 5,000 or 6,000 employees in that building. Maybe 200 of them doing material science, 300 doing physics. It's a private institution, and there was no tenure and no graduate students. And so, but many scientists having different expertise, each one with his own lab. But to get an experiment done, you had to collaborate with someone who who hopefully was your friend, you would go out and make collaborations with other people who had different expertise to put together what you needed to do for that particular experiment. So collaborations were forming and dissolving all the time. The other thing that was marvelous about the labs is that the management thought that individual scientists, such as myself, were best positioned to figure out what I should do next. In other words, what problem should I address? And they thought that scientists who was close to the data could see better the opportunities in the future and should just go and do it. So I made some radical changes in my direction during when I was there, and all I had to do was go and talk to my department head for about 30 minutes, have some discussion of going forward. I didn't have a budget. He would provide what I needed, at least to some extent. Okay. Also, it was interested in different fields of science, and so, there were certain, at that time, when I first went to work in 1970, 1980, there were certain projects, types of things that were important in chemistry, and they were not necessarily the same things that were important in this long-range research with respect to communications. So they were interested in problems that you could not get funded from the NSF, or it was irrelevant whether you could get funded by the NSF. In fact, what I'm going to talk about, you could not get funded because nobody in academic life thought this was an important problem at that time when I started, and so when it went for peer review in the NSF, nothing would happen. That was a great advantage. The advantage I had was that it turned out to be a good science problem that could not be funded anywhere else, more or less. And I had opened this wide collaboration with other people in the same building. If I could convince them it was a good problem to work on, at least transiently, for the particular experiment. All right, here we go. So this is a picture that's supposed to show the advances in semiconductor chip development over a period of time. And this is a transistor. It's a piece of silicon right here. And then the two electrical contacts, the source and the drain here. I guess this is a gate underneath it. And you see the scale here. This is 50 nanometers across. This is 2003. Going forward, getting smaller all the time. Here's 10 nanometers across. And here is, so this is a projection forward. And this is some kind of fanciful idea about what might happen if you went way out in the future here to where we are now. Maybe you could make a transistor out of a carbon nanotube or some kind of small thing, piece of nanotechnology. The main thing which has made computers and communications so much better now than in those days is miniaturization. Miniaturization has changed everything in human society and much as well as here. Human society has been totally transformed, as well as research has been totally transformed by having cheap computers everywhere, by sending messages around the world on optical fibers with no cost, essentially. This is, oops, backwards. Well, I'm not going backwards. Let's see if I am going backwards, I guess. It makes big jumps, this thing, okay. So in preparation for my talk in Sweden, I looked up the modern state of transistor development. Everyone here has a cell phone, maybe an Apple cell phone. Apple cell phone has an M1 chip or its successors, designed by the Apple Corporation in it. That chip has 110, what does it say here? 114 billion transistors on one chip. It's just not random transistors. It's transistors which are designed into a circuit, purposeful circuit to accomplish something. This is what miniaturization can do for you. Make this huge, huge, complex thinking machine in such a small area, and it can do it cheaply. The chip might cost $200 or something like that. It's a tremendous, tremendous, tremendous accomplishment of the human mind to get this done. In my mind, I think of it in the same way as the progression in DNA technology. DNA technology has progressed also from scratch, to the point now where it's permeating all of medicine, and it's used in criminology. It's used in the study of ancient man. We now have the complete genome of Neanderthals from extracting DNA out of the teeth of fossils. All of that because of understanding the DNA and the mechanism of heredity. Great accomplishment, changed society, as well as this progression in the electronics. Okay, so now we come to what is a quantum dot, or what did I work on? And I'll describe that in stages. And so basically what goes on is there's some kind of reaction in a liquid between, in this case, we want to make a transistor, which is cadmium selenide, which are two different atoms. And so you have two reagents, cadmium and a selenium reagent, that react with each other under appropriate conditions. And most of the work has been figuring out what are the appropriate conditions to make this small crystallite, a small piece of rock. And you can see from the picture here, this is maybe 10 atoms across from one side to the other. And maybe 40% of the atoms are actually on the surface. It's a tetrahedral material that cadmium is surrounded by 4 seleniums in a tetrahedron. Selenium is surrounded by 4 cadmiums in a tetrahedron, like diamond, like methane. With methane is tetrahedral, silicon carbon is tetrahedral with 4 hydrogens around it. It's the same sp3 bonding. So let me say a little bit about precipitation, since this is basically analogous to the old, when I was a young student, they were just abandoning teaching quantitative analysis in chemistry school, in chemistry graduate school, or undergraduates. And in quantitative analysis, there were a whole series of precipitation reactions using sulfide to figure out if you had a sample with unknown metals in it. Then there were the reagents you used, and to precipitate different metals in different conditions, and you could figure out roughly what was in the sample. So what is precipitation? A good example is, I can make an aqueous solution of cadmium sulfate. It's a salt, it dissolves in water, no problem, the solution is clear. I could also make a solution of hydrogen sulfide, or maybe hydrogen sulfide is a good example. Sodium sulfide is the best example. Make an aqueous solution of these 2 salts. They dissolve as ions. There's no problem. You have an equilibrium. So what happens when you pour those 2 solutions together? The cadmium ions see the sulfide ions for the first time as you mix the solutions. And it turns out that cadmium sulfide is not soluble in water. So it immediately begins to aggregate and make really tiny little nuclei, and then if you wait long enough, you'll get a bigger aggregation, and the color will change because the initial solutions are clear, but when the precipitate begins to form, it has the color of the precipitate. And so cadmium sulfide absorbs in the blue, and so the solution turns yellow. You can just follow with your eyes as the crystallites form. Ancient precipitation reaction, okay? So what we're doing now is making very small crystallites by chemical process from the individual components, the same way as that precipitation, but just in a much more sophisticated manner to control the whole process. All right. And so you can see in the you make this crystallite, but it's in a liquid, and it's covered with ligands on the surface like this, and the ligands are critical because they bind to the surface atoms. Surface atoms have broken valence. You know, an atom on the inside has the correct valence, 4 bonds to 4 nearest neighbors. An atom on the surface has 3 bonds into the crystallite and 1 bond sticking out into the liquid, one electron. You know, it's a broken bond, and you need to do something with that, and you can absorb a ligand on the outside, and the ligands control the electronic properties to some extent, and they control solubility. You can make particles that are soluble in fats or in all kinds of different environments by just control of these ligands. A lot of our time has been spent working through that. All right. So this was, for me, an accidental observation. And so I put up this first paper just to show you what we were doing at that time. I am a laser spectroscopist, was a laser spectroscopist, and I was trying to do an experiment to look at the organic chemistry on the surfaces of semiconductors. You know, in a semiconductor, as I say, you can excite it with light, and it makes an electron or a hole, and either one can come to the surface, and so you have the potential to either oxidize or reduce something which is on the surface, depending on circumstances. So you can do that with the bulk electrode, shine a laser on the surface and get some kind of signal off of it. Much better to do it in a colloid, because in a colloid you have a much higher surface area than on a flat piece of the bulk material. All these little particles, you can absorb on them, you know, and then it's actually optically homogeneous medium. You can shine the laser beam right through it. It's like a molecular solution, basically. You can shine the beam through it and cause this photochemistry to occur. So we were trying to do that. And I began to make these cadmium sulfide solutions by the recipes which were in the literature. And I noticed that occasionally in the first day of making this colloid, the optical spectrum was not quite right, you know. And so this is the absorbance, and if you have a bulk piece of cadmium sulfide, it absorbs in the blue and it comes down, and it has a threshold about 5,000 angstroms. And that's true of big particles, experimentally. But if you make these smaller particles, the 45 angstrom particles, the edge shifts to the blue, and you get a little kind of bump there. And that was an exciton. So I didn't know what this meant, and it took a while to sort of sort out why this spectrum was changing. And I finally figured out in principle it was changing because we had entered some kind of intermediate regime where the properties were no longer like bulk semiconductors. Getting small enough to behave something like a molecule. It was hybrid between a molecule and a bulk semiconductor. Transition region. If you got down to maybe a cluster with 10 or 15 atoms, it's entirely a molecule, and describe it in that language. And a piece of solid that's maybe 200 angstroms in diameter is entirely a bulk crystal. But there's a transition in there going up like that. And moreover, the transition would be important because of this miniaturization. You know, so we were thinking about this in the 1980s, and they were just starting on this progression of the smaller and smaller transistors. And we knew at some point in the future, things would get to be so small that we would enter this regime where things began to change because the semiconductor was acquiring molecular characteristics. Didn't know how far it could have been 10 years, it could have been 40 years. You know, only God knows how fast the progress would occur. But in principle, there was a scientific issue there that was important to the industry. So that's the best kind of research to do. You know, basic research, which is in fact relevant to somebody cares about somewhere. I mean, if you can find a problem which you can do basic, you know, there's some problems that are only basic research and some that are only development. But if you can find a problem which is half and half or is relevant to both communities, then that's marvelous. And it was relevant to Bell Labs, where I was. So we made these small particles, and we found out that the optical spectrum was changing like this, and we took the Raman spectrum of the liquid, and the Raman spectrum showed these sharp vibrational peaks, and that was a proof that the particles we were making are crystalline and not amorphous. So it was just a small particle of crystalline cadmium sulfide, but the spectrum is changing because it was small, not because the bonding was screwed up or something like that, you know. Okay, so thinking about it, this evolution from molecules to bulk crystals. So we started to think about what we had to do with this, or you know, what are the important issues? And intellectual challenge, how to describe the properties in this small size using ideas from physics or ideas from chemistry or both or neither. You know, that's one issue to work out. More important is the synthetic challenge, is can we make a size that we want to study somehow? And can we make it well so that the surface is controlled and it's crystalline and not amorphous? This is all Edisonian in the sense that nobody really knew how to do this, and we were just trying to figure out ways to do this. And then we want, since all these properties function as a function of size, need to characterize them and need to actually characterize them one at a time, or at least one size at a time. A colloid itself, you know, it has an average diameter. It may be large or small, but it has a range of sizes around the average diameter. And so whenever you measure a property of that sample, it's got some larger particles in it, some smaller particles in it, as well as the main size in there. And when so the property that you measured is broadened by the size distribution, because it has more than one size. Got to try to eliminate that somehow. And then the technology challenge, can you, so in the language of chemistry, it's true that these nanocrystals are new families of large molecules, not previously known. And can we use them for something somehow? You know, that's always comes up. And they would only be useful, actually, if you could get the quality up high, you know. It would have to be cheap to make, and then you have to figure out good ways to make high-quality particles rather than poor-quality particles. Then they might be useful to somebody. All right, so this is to prove to people, especially people from a physics background, that this actually is a branch of chemistry. And so let me show you how this is done. Three-neck flask here under argon, and in the bottom is maybe 15 cc's of solvent, and that the reaction will go on in there. And this is a thermocouple coming in from the sides, and a heating mantle on the bottom to adjust the temperature, and a septum on this side, so we can inject chemicals, initiate the reaction by injecting chemicals through the septum into the liquid. I used to tell friends that for every hour we spent doing spectroscopy, we spent 4 hours doing synthesis. Because that, you know, no point in doing spectroscopy on a lousy sample, and you need to have a good sample to actually invest the time to do spectroscopy on it. All right, here's an example of, so let me go back to this thing, and so you might inject the chemicals to begin with to make cadmium sulfide. And then you stop and you have cadmium sulfide of a certain size. And then you could change, at that point, you could change the chemicals that you inject. And you could instead inject chemicals to make cadmium selenide. Different semiconductor, close but different. And if you do it correctly, if you make the second injection slowly, you won't make any particles of cadmium selenide, but the reagents, as they come down, they'll grow on the surface of the particles that are already there. So then you make a core shell structure by sequential addition of chemicals. And let's go, okay. So here's an example of a core shell structure. 3 different semiconductors, sulfide, selenide, and zinc sulfide. And you see they've been injected, starting with cadmium selenide, and then the final stage, zinc sulfide, and it makes a coarse shell structure like this. If you do it slowly, it makes a fairly good coarse shell structure. So that gives you some possibility. For example, this material absorbs green and red light, makes an electron in a hole, but the zinc sulfide is almost transparent. It's almost an insulator. So if there's an electron on the inside here, it can't get out to the surface into the liquid because there's basically an insulator around the surface of the particle. You know, it's like silicon microelectronics. Silicon, anything you make out of silicon only works well because you can put an oxide onto the surface. Oxide is simple to make, and it's a very good insulator for keeping the electrons and holes on the inside of the silicon. And this shows carboxylic acid. There's a ligand on the outside here. Again, you remember there's broken valence in these atoms. These are cadmium atoms on the surface, and you can make this kind of carboxylic acid. You can do many other things as well, but this shows you it's done in a liquid, and naturally there's ligands on the surface. All right, so let me go a little deeper now into the chemistry of this. So we're talking about precipitation from reagents, and the problem with that is if you just do that in water or a pure solvent, you'll get massive aggregation of the crystallites, because crystallites are reactive on the surface, broken valence on the surface. So when one diffuses up and touches another one, it will fuse across the boundary. And then you'll have a dumbbell-shaped, larger crystallite, and you'll get kind of diffusion of others coming in, and you'll make a big mess. You know, fractal or arbitrary. You don't want that. You want to have individual crystallites, and you can study them one at a time. We wanted to study the size dependence of individual crystallites. So one of the first things we did is make micelle solutions and try to do the precipitation in micelles. So a micelle solution is, you know, it might be 99% heptane and 1% water with enough soap in there to make a boundary layer between them. You get a spontaneous phase separation. You'll get many small droplets of water, 50 angstroms across, each one surrounded by soap, and each one in the hydrocarbon solvent. So the idea was we would put maybe 10 or 25 cadmium ions in each water pool. You know, that's the amount of cadmium. Then we'd add, in this case, an organoselenium reagent, which would hydrolyze when it saw the water here and start the precipitation, and you get a little crystallite like this, one in each bubble. And that would be protected from aggregation because the bubble structure would, you know, if this came up against another one like that, the micelle bubble structure would prevent them from fusing across the boundary. So that worked. And we could, in fact, see, you know, start the reaction is initially colorless, start the reaction, color develops, put that in the optical spectrometer, see where the band gap was, and give you a rough idea of what the size was. Then we figured that these were, I guess in the language of polymer science, living polymers. You go through this, make a crystallite, and then you could wait an hour, and then you could slowly add more cadmium and selenium reagent, and they would, again, not form a new particle, but they would deposit on the surface of the old one and grow the lattice larger. So you could do this, and you could make particles, and you could stop, take the optical absorption spectrum, add a little bit more reagents, it would grow larger, take the spectrum again, band gap shifted further to the red. You could follow what was going on. And then we figured out if the surface is in fact reactive like this, we could do some kind of exotic chemistry, besides just make it larger. Oh, I'm sorry, I'm on the wrong way here. So you could take, I'm skipping over some steps here, but you could take particles that existed in the micelles, and then you could add a reagent at the end here. You could add phenyl trisilylselenide, and so what would happen is that would come down and it would deposit on the surface, and instead it would leave a phenyl group bonded to the selenium on the surface. So you have particles that are just as they're made. They have bare surfaces. I mean, there's water in there, and they're hydrophilic, and they stay in the water pools. But you coat the surface with these covalent phenyl radicals like this, it becomes hydrophobic. Falls out. It just falls out of the solution, and you get on the bottom of the beaker, you have this pale yellow powder. That's the quantum dot which you've made. That gives you the opportunity to remove it from the solvent and to characterize it. So you would end up with a pale yellow powder coming from the precipitation. The powder with phenyl radical on the surface. And then we tried all kinds of things using intuition. My collaborator, Mike Steigerwald, was very important in this. What we might further do on the surface. And we were thinking that, well, there's the phenyl radicals that are bonded to selenium on the surface, but in principle, the cadmium is bare on the surface. We should put something that would make a Lewis bond base to the cadmium on the surface. And so we tried the idea that this pale yellow powder would be soluble in pyridine. And that worked. You could take this, when I mean soluble, I don't mean going back to atoms. I mean just the particles themselves would go into solution without breaking up. Okay? And I remember that one of the first experiments we did, we dissolved these particles in 4-ethylpyridine, and then we reflux them. The boiling point is 160 centigrade or something like that. And so we reflux this solution. And the color changed a little bit to the eye, as it's refluxing. Cool it back down and take the optical absorption spectrum again, and it had improved, meaning that it got sharper. And then we would take that and do the X-ray diffraction on these particles that had been refluxed, and the X-ray diffraction was better. So that we were making crystalline particles to begin with, but they were full of defects because it was a room temperature synthesis. I mean, these semiconductors are normally made only at high temperature. So we were making these particles, and in the Raman, they were more or less crystalline, but they had a lot of defects in them, and that broadened the features. You reflux at higher temperature, and it anneals out the defects which are on the inside, makes a more nearly perfect single crystal. That improves all the properties that you would measure. So we discovered by accident this way. So then we began to explore higher temperatures and more different solvents. Here's an experiment. 3 hours at 230 centigrade involving a solvent which is 90% tributylphosphine and 10% tributylphosphine oxide, and that made a really good sample. And again, this is found by trial and error. And 30 angstrom diameter, and they're capped by this phosphine oxide, the oxygen forming a native bond to the surface, in principle. Very nice. We did a lot of characterization on this particle. I won't show you all of that. But again, because it was Bell Labs and I had friends who had different scientific expertise, we did the transmission, we did microscope studies on these things, powder X-ray pattern, selenium NMR, XFs, in Brookhaven, we did XAFs with Matt Marcus, trying to get a good characterization of them. Oh, I keep turning this back the wrong way. And this is a slide to show you that when things work well, you can make spectacularly good particles. Now, this is not my work, but this is Chris Murray, who's a professor at Penn. And at the time he did this, he was at IBM in Yorktown Heights. So these are lead selenide quantum dots, actually cubes, which are maybe 100 angstroms in diameter. And you can see they're more or less all the same and more or less all perfect. And here's a high resolution image. And so you see the individual lattice planes as the electrons are looking through the sample. Really nice to see that after a lot of hard work to get good samples, you know. Now let me go back into the molecular orbital theory of these materials and why is it that you get these optical changes. Well, the most important thing is the fact that the chemical bonding is the same. It's tetrahedral chemical bonding, sp3 hybridization. That's true in small molecules involving the silicon and also true in the bulk crystal. And so I've shifted to silicon here. And here's disilane, you know, silicon-silicon bond with capped, if you will, by hydrogens on the silicon to preserve the tetrahedral valence. Okay. And so you can think of a crystal like this as, to begin with, it had, all right, so this has a sigma bond here between the two silicons. Just like you teach in freshman chemistry, sigma bond with 2 electrons in it, spin up and spin down. And it also has an anti-bonding state, you know, way up in energy, which does not have any electrons in it, but it exists. It exists. All right, let's go to the next slide. And here, this shows the evolution of the molecular orbitals in a schematic sense, going from one silicon atom here, S and P orbitals, and then if you have sp3 hybridization, it shows the orbitals in a tetrahedral pattern for the one silicon. And now this is a picture of what happens. You see, this is one red dot, this is one silicon. This is two red dots, silicon next to a silicon, forming this sigma bond, the way we describe it, you know, coherent overlap with no node down the center and 2 electrons in there. And that's this level right here. There also exists this anti-bonding orbital up here, sigma star, with a node down the center, and it's not populated. It has no electrons in it. It's an excited state, so to speak. Now, when you get to a cluster, suppose you have one of these clusters I just showed you that has maybe 50 silicons in it or something like that. Then what you have is, in fact, 50 of these bonding orbitals and 50 of these anti-bonding orbitals, one from each local pair. And because they're next to each other, they couple together to make molecular orbitals that extend over the entire crystallite. You know, this is just like in hydrocarbon bonding. You have molecular orbitals that extend over the entire molecule, and it's the same thing here. So you have a lot of silicon-silicon orbitals that extend over the molecule, each one with 2 electrons in it. And some of them are higher than the initial orbital. Some of them are lower like that. So they're spreading out. The more silicon atoms you add, the more spread you get in between the higher and the lower orbitals like this. And so this is, in fact, the highest molecular orbital of the cluster. I'm ignoring the surface for the moment. I'm just talking about silicon. But you also have the same process going on with these excited orbitals, which are anti-bonding. There are no electrons up here. This is a LUMO of the cluster. As the thing gets bigger and bigger, you get more and more molecular orbitals, they get closer and closer together in energy. You can have 1 million orbitals, you can have 10 million orbitals. So they're so close to each other that they form a continuum. Can't really identify the individual orbitals anymore. They overlap with respect to thermal width or something like that. And that in the limit of the bulk crystal, but they don't spread out indefinitely. There's an asymptotic limit here, and you get this range of continuous occupied orbitals. In the language of physics, that's the valence band of the semiconductor. And you also have this region of continuous antibonding orbitals with no electrons. That's the conduction band of the silicon. So this shows you how you go from a small cluster and individual orbitals to the bulk solid in a very schematic way. So the predictions of this kind of picture are that this is the band gap of the bulk solid, the band gap of material, or it's a homolumo transition of the bulk material. This is a homolumo transition of the cluster. And the way I've drawn the picture, you can see it is larger. That is the quantum size effect. The threshold for optical absorption shifts blue if it's not large enough to be a bulk crystal because of this argument. The other thing is that a small cluster, you have the potential of seeing the individual optical absorption peaks. Everything is on top of each other and it's continuous absorption. But when you get small, there are these individual transitions from one molecular orbital to the other, and so they make individual electronic states, and they may be close. So you may have two transitions which are close and partially overlap, but you begin to see peaks in the absorption spectrum, partially resolved peaks as things get small. The individual molecular orbital it's like an aromatic hydrocarbon. Aromatic hydrocarbon, you have a number of pi star transitions. And in a big hydrocarbon, you have a lot of states that are close to each other. Small hydrocarbon like benzene or naphthalene, you have one or two transitions that are well resolved. As the hydrocarbon gets bigger, more transitions, and they tend to merge with each other. Same idea. This is three-dimensional polymerization. I haven't even talked about that. Okay. So this is a simple theory. There's also a way of dealing with this coming from solid-state physics called the quantum size effect. And that is based on, that's an approximate method. This is an approximate method. Here, an approximate method that starts with molecular ideas that's very small size and comes up to this intermediate regime. You can also start with solid-state physics ideas. You can start with the band structure of the material and then take approximations to bring it back to this. That's called quantum size effect. Either they are functionally equivalent descriptions. Mathematically, they're equivalent. All right, let's go on a little bit. So here's what comes out of this. And if you had a material, a semiconductor, cadmium sulfide, so this is the absorption threshold, 2.7 electron volts for the bulk material. And then when you get small, it begins to go up like that. And so this is the part of the Hamiltonian that, my ear is popping a little bit. This is the part of the Hamiltonian that takes the molecular orbital part. There's also another part of the Hamiltonian, or what goes on in the small particle that I haven't talked about, but that's the Coulomb attraction between the electron and the hole. So you absorb one photon by a particle. It goes up like this. You have both an electron and a hole in each other, and they have opposite charge, and they attract each other. And so they're orbiting around inside in an orbital, but they attract each other. There's a Coulomb attraction energy that pulls the band gap down, where the molecular orbital effects are pushing the band gap up. So both of them are in there, and one of them, the orbital effects Sorry, let's go back. This thing, I have trouble with this thing. The orbital effects make a larger band gap like this. That's a dominant effect at small size. But there's also this increased attraction that pulls this band gap a little bit below, actually, the bulk band gap. So what it actually does, it comes down like this, it goes below, and then it comes back up to the asymptotic limit. All of this can be calculated with classical ideas. The advantage of this quantum size effect model, you just have to know the curvature of the bands, or basically the strength of the chemical bonding, and you can calculate the blue shift. If you know the curvature of the bands and you know the dielectric constant of the material, you have the input you need to calculate where the band gap should be for any size. So that's approximately correct. And the advantage is there are no adjustable parameters. It's based entirely on things that are known in the bulk crystal. So based on this initial thing, you can predict what the band gap is and the structure for the small particles. At least to begin with, it's like first order perturbation theory. Okay. All right, so that's a very shortened version of the main things we did. And I had two very strong postdocs, among others. One was Wuji Buendi, that I shared the Nobel Prize with, and he went to MIT, assistant professor, and the other one was Paul Alvasados, who went to Berkeley as an assistant professor. And they took these ideas to academic life, and they had large groups of graduate students. And so after a bit of time, many students were trained in this. More and more students were trained, and it grew to be a large field. And people began to experiment with this synthetic chemistry all over the world, you know. Too big for me to keep track of. All right. But if you think about nanoscience in general, the question I'm always asking is, what are the electrons doing in a specific problem, you know? There are other things going on in this inorganic nanoscience which are different and equally as interesting. So much trouble with this. Yeah, let me just start with this slide. So here's our quantum dot again. And you have an electron in a hole is on the inside, and it suffers the electron suffers a quantum size effect, which is basically formation of molecular orbitals off the walls. That's a single electron effect, a molecular orbital effect. But here's a carbon nanotube. How many people here know what carbon nanotubes are or have some familiarity with them? Okay. It's a really interesting problem, you know. It was discovered by Jima. Jima is a electron microscope person for, I think, Toshiba or someplace like that in Japan. And what they did was they would run a carbon arc in vacuum, you know, two pieces of graphite. Huge current flows through them, and it's in helium or argon or something like that, and there's a plasma formed in between. Then they'd stop. And then he would look carefully at the surfaces of the two carbon electrodes. And he would find these carbon nanotubes growing and sticking out into space. By accident, he found this. Everyone knows what graphene is like. It's sheets of carbon atoms, hexagonal carbon atoms. It's like benzene polymerized with no hydrogen atoms. A local hexagonal structure. It's infinite in 2 dimensions, and it has certain band structure and so forth, and that's been known for many years. But and so what he found was a derivative of that. What you can do is, as an intellectual exercise, you can, with a scissors, cut a strip of the graphene out. So it's a long, flat strip of the graphene like this, at a certain width. and then you fold it back on itself like it's trying to make a tube. And so for certain angles and for certain angles and for certain diameters, as you fold it back on itself, there's broken valence on the edge of the strips. Well, there's no broken valence in the middle. It's one wide strip with broken valence on this end and on this end. Fold it back on itself, and the broken valences will match up exactly because of the crystalline structure, and it will seal. And so it's like a rolled up piece of graphite, small, and but different. One dimension, it's continuous in one dimension and has a short dimension in short dimension in 2 dimensions. And so this shows a section of one of these things. And this is supposed to run to infinity both directions like this. And so you can, so in graphene you have pi electrons. Graphene carries current by graphite carries current running through the pi electrons down the surface. And so here you have pi electrons that are all on the surface here. So this carbon would have it has 3 bonds into the lattice and one broken. One occupied and unoccupied pi orbital sticking out into space. In the same way naphthalene does. If you have an aromatic hydrocarbon, there are p orbitals sticking up like this that are not involved in the bonding, okay? Not involved in the sigma bonding. Okay, so if an electron, so much trouble. So if an electron, so Bohr's original idea for bonding in the hydrogen atom was that you put an electron in an s orbital in a hydrogen atom, and it runs around in a big circuit, in the circumference of the s orbital, and basically it comes back on itself on the other side, and it has to form a coherent overlap. It has to be a complete wavelength, not a half. So you can have one wave going around in the orbital. You can have 1 electron or 2 electrons. How to say it? You can have the wavelength of the electron that's 1 complete lap or 2 complete laps, but you cannot have a state that has, say, 1.47 overlaps or something like that. So that was Bohr's idea to create quantization. The electron had to interfere coherently with itself when it came back around the orbital. This is invented 20 years before Schrödinger equation. Something similar is going on here. If you have an electron in the pi system here, and it's going around the circumference like this, it comes back on itself, and it has to have a coherent overlap. So that means that there's only certain wavelengths of the electrons that are allowed to go along the circumference like this. 1 wavelength, 2, 3, a series of states that are separated in energy. But if you have an electron that's just running down the surface, running down the tube like that on the surface, it's an infinite system, and the electron just goes and it doesn't have to interfere with itself. So there, the energy levels of the electron are continuous if it runs down the surface. So you have 2 types of orbitals. You have a series of discrete states pointing out like this, and you have continuous energies for electrons running down the surface like that. It's a one-dimensional wire, basically. That's a very good system, and a very good system for carrying electricity. It has very high mobility. The electron can really go down the surface with nothing to stop it, because there are no defects. It's a perfect crystalline system. The only scattering can come from if the carbon nanotube is laying on something else. But carbon vacuum has electrons extremely, extremely mobile. This also has strong correlation because if you put two electrons in this system, they can repel each other. One goes this way, one goes that way. And so their behavior is correlated. They want to avoid each other, two electrons. Correspondingly, you put an electron in a hole in the system, and they'll be attracted to each other in a one-dimensional system like this. It's very hard for them to avoid each other in that way because they're coming down each other, and the carbon nanotube are basically too small for them to avoid each other. That makes a system that shows very high electron correlation. And I just put this up in order to show you that there are other things going on which are really interesting. Much of modern solid-state physics is based on correlated electron systems, which are two-dimensional or one-dimensional, as opposed to three-dimensional. Okay? So this is just a taste of what can go on. Let me go to the next slide if I can. And I'll skip this. This is because this is a more detailed interaction of, oh yeah, another thing. Let me go here. This is interesting. I'll just talk about this. If you have a small tube or just a single sheet of material like tungsten diselenide, you create an electron hole, and they attract each other, but the attraction is screened by the dielectric constant of the material. But as electron and holes separate, more of the field goes out into the vacuum and less going through the material. So that means the strength of the Coulomb interaction depends upon, it's not a 1/r dependence. It depends upon the distance they're apart, actually, it's not 1/r. And so carbon nanotube has this in spades because the electrons are in the pi orbitals on the surface, So if you have two electrons or electron in a hole, part of the field is going out into the vacuum. So that means the properties of the carbon nanotube depend upon the solvent it's in, as well as if there's any, as well as they're different in vacuum than they are in solvent, because the electric field is fringing out of the material. These are old problems in electrostatics, but they have new currency because of they're really applicable to these small particles. All right. So going towards conclusion, in properties in the particles, the quantum dots, size-dependent properties from simple quantum confinement, essentially no correlation. But as I said, these nanocrystals, if you can make them, and especially if you can make core shell particles, there are entire new classes of molecules that you can do things with. People use them a lot for electron donors. And the carbon nanotubes are superb molecular wires. And if you think about this as an experimental field, it's relatively easy to do the theory. What's hard is to make a good sample. And so the critical thing is to make a sample and to put the sample where you want it. Because you may damage the sample when you transfer it or something like that. Best thing is to synthesize it in place. That's the same problem which exists in semiconductor chips. They make this really complicated structure of all of the different transistors, and they're connected up by little wires. And you have to make them in place in the right position so that they naturally form a circuit. This is done by photolithography. So as I tried to explain, I was able to do a lot of this in Bell Labs because of the collaboration, people with different backgrounds. And here are some of the people I worked with in Bell Labs. Steve Bougie was a postdoc, as I said. He shared the Nobel Prize with me for the work he did at MIT. And at Columbia, I've worked mostly on this strong correlation, and with these collaborators, it's been very good. And I've had some strong students, which is always marvelous. All right, so this is the last slide. Maybe 15, 20 years ago, I was at a symposium, I think it was Singapore, and it lasted 4 or 5 days. And then when I got there on a Friday, they told me that, well, I had to give a little talk to high school students on Saturday morning, along with other people, and I was supposed to talk about so the room was full of high school students from Singapore, maybe 3 times as many as in this room. And I was supposed to talk a little bit about what it takes to make a good scientist or something like that. So this is what I put up after I went home and wrote this Friday night, and we're all trapped by our educational backgrounds. That means you know one area of science, you may know a branch of chemistry. You don't know much about what goes on in the rest of chemistry. You certainly don't know what goes on in other areas of science. It's just all of that is overwhelming. It's not a problem for undergraduates. The most important thing to do is you must learn one area of science well before you can think about extending your education. But one way to deal with it is to pay attention to your friends and collaborators and try to teach yourself something new every day. So what I would do is, other people have done this well. You could take Friday afternoon and stop work on your thesis or what you were doing, go into the library, read scientific articles that were interesting, that were not connected with your research in a different area. Just invest time to learn a little bit about this other area. And if you're an undergraduate and you're going on to graduate school, that will give you some help in figuring out which professor you wanted to work for when you got there. This reading, that would expose to you other areas of science. You could do it again if you left graduate school, became a postdoc, do it again, change fields based on problems that you found from your reading that you didn't know about when you started. And that would make you a much, much better scientist. Why are your colleagues working and why is it important? So I would always ask people what they were working on. And it's obvious they thought that was an important problem because they were working on it. And not necessarily interesting to me. I didn't have to think it was a good problem. But I listened to them and found out why they thought it was an important problem, and that way I could get a broader understanding of science. That's a much better way of learning than it is just to try and get it from random articles or things like that. Problems difficult in one field are easy in other fields, that's for sure. There have been some people with physics backgrounds who have tried to work in this area without any knowledge of chemistry. And they have suffered because they didn't understand molecular orbital theory. They didn't understand anything about ligands or localized states, But they tried, in the physics culture, what you would do is you would try to invent that from scratch. Figure the problem out for yourself from scratch if you didn't know the answer. But the answers were already known in chemistry. The reverse is also true. A lot of chemists try to figure things out, and the problem has been well worked over in physics or in material science culture. This is what you gain by having a broad exposure to begin with. And the last thing is, to be a good scientist, you have to have discipline, patience, and discipline, and dedication, all these things. But you don't have to be a genius. That's for absolutely sure. You can make all kinds of mistakes go along the way. Most important discoveries come from accidental observations. And you don't have to be a genius. I mean, some are geniuses like Linus Pauling and so forth. But most people who discover something important, they found the problem was considered to be important by the rest of the scientific community. And they had the patience to work on it in the beginning when other people were not working on it. And then you had just by yourself and then some time to make progress in the field before the competition got to be really huge. So Thanks for your attention, and I'm happy I could speak to all of you.
Professor Brus, thank you very much for your talk. It was really inspiring. We have time for one or two questions.
Sure.
From the students and public. If anybody has a question, here it's a mic. Anybody? Yeah, there one.
Just gotta give me a second.
No, you go over. Yeah, you go around. Okay.
So
It's coming. The mic is coming.
I'm going to get this chair and move it up.
Yeah. Please.
Hello? Oh,
Okay. You go.
okay. Thank you very much for the talk.
He's there. Stand up.
Stand up, yeah.
Thank you very much for the talk. I am Anthony. I would say to win a Nobel Prize means like you really understand things very well. And this is just a general question that to you, at what point do you think to yourself or you convince yourself that you really understand something?
So there are different answers to that question, and my professor, when I was a graduate student, said, well, if someone asks you a question and you have to go to a textbook to try and look up the answer, then you don't understand it. I mean, I don't mean here just some number like the density of lead, but if you need to go to textbook and find where the problem is worked out, well, you understand part of it, but you don't really understand it well. But if your response is somebody gives you a problem and you want to walk to the blackboard and pick up a piece of chalk and work it out right then and there on the board, then you really do understand it well. But there are different levels of depth all the time. So you never understand something completely. I mean, the language that people use to describe chemistry is approximate. And you could go deeper into this, what all the electrons are doing all the time and stuff like this, and molecular dynamics. But after it, I mean, that's the way it works.
We have one more question from there. It's only one more. You can talk during the lunch after the dinner, sorry. We start again with lunch, guys. Don't worry.
Great talk, and thank you for coming. I hope everybody can hear me. So I kind of had two questions. I'll try to make it as quick as possible. One of them is, you said in certain parts you used intuition, and I was wondering if there were other parts that were used that weren't necessarily from a book. Like, did certain things come to you in dreams? Because to win a Nobel Prize, I'm sure there were certain things that maybe didn't come from a book. So I was just wondering that. And then the second piece was, in your opinion, do you feel as though it's possible that trees could be the cause of mental health issues? Meaning that, do you think it's possible that male trees may produce a different type of oxygen from female trees, and with the fact that there's few female trees in cities, could it, to some extent, destabilize the atmosphere and make it off? You know, when males reproduce, they use a base, females use an acid, it neutralizes it. Is it possible for the air to be non-neutral, based on your idea of chemistry, because maybe the male trees might produce O2 negative superoxide, and then we may have, the female trees producing something, and now in some way it makes it neutral. In your opinion, do you think it's possible based on your knowledge of chemistry?
Well, I've never heard anyone propose that. But I would not rule it out, because new things are being discovered all the time. I mean, it was just some 10 years ago that people discovered that diatomic molecule nitrous oxide, NO, is actually a signal molecule used in the human body. When I was young, somebody would have said, "You're nuts," if you had proposed NO was an important molecule in the human body, So things that get discovered all the time. It's obvious that genetics plays a really huge role here. Genes are different in men and women, and I would look at that first. There's signaling, like you say. There is a famous woman who is a woman who works on the forest. I can't remember the name, but she works on trees, and she's a professor in British Columbia. And so, the idea we have about trees is a tree grows, it has a root system, that brings nutrients up like this, and it's a separate system from the tree over there. But she showed, she used isotopic, and so the tree is producing, what does the tree produces? It produces oxygen, right? And takes in carbon dioxide from the atmosphere. And she used a chemical method, isotopic substitution, and she showed that, in fact, trees which are fairly far apart are connected by root system under the ground like this, by fibrous roots. And so that if one tree is not healthy, it sends alarm signals to the tree over here. And in fact, it even sends molecules, so that if you let's say, I guess the experiment I'm trying to recall is you grow one tree using isotopically enabled carbon dioxide, and you grow the tree next to it using ordinary carbon dioxide, and there's a plastic bag in between so that they're not exchanging the atmosphere. The product over here will be influenced by the isotopes from the other tree. So there's actually transfer of reagent molecules through the root system. That was unexpected discovery. Really interesting, The plants in the forest are so well connected one to the next. They send distress signals from one to the next. They send food from one to the next. That's an example of something that could happen, and does happen periodically. And so I guess to your first question, many scientists report that they have their best ideas in the shower, right? And it's true. If your mind, and it's also true, I'm certain that if your mind works on problems overnight when you're sleeping. So you've got a problem you've been dealing with all day, you don't know what the heck to do with it, and so forth. And in the morning when you wake up, there will be a new idea in your head that just pops up. And I think that's the result of 8 hours sleep, your mind working on a problem, trying to make associations and so forth. So that's part of intuition. In chemistry, intuition is based on experience a lot. Chemists have a certain idea how the world works and what's feasible, what's not feasible, so that a senior professor can make a much better educated guess about something than the beginning graduate student, just because of experience, not because he's smarter or anything like that, but just because he has all this experience in his head, and he draws on that. Not true in other fields, but it's true in chemistry to some extent.
Okay, thank you very much. So, now we are moving to the next part, which are it's award ceremony. Please stay, don't go away. You might we might be the winner. And I want to thank again to Professor Brus, because he will help me to give the awards. So even if we didn't met in the last 6 years, we gave the awards, yes? And we start even new awards in the meantime. So PhD Student Teaching Award, it's for the first time offered this year to a student which have outstanding teaching, a PhD student which have outstanding teaching. And this year is going to Gabriela Ravin, which is who is a great person, but unfortunately she had a car accident a few weeks ago, and I will invite Professor Ed Canali to accept in her behalf this award. So this is a diploma. Oh, yeah, sorry. It's a diploma.
So,
Yes.
congratulations to your student.
Thank you. So congratulations. Okay. Next award, it's for John Paul Clay for excellence in academic excellence, outstanding academic potential, graduate with a high GPA in BS or BA, and is going this year to Nidhi Nobel. Nidhi, please come up. So, this is okay, these awards have a monetary component. Please do the paperwork, and the money will be delivered direct to your account. Yes? Oops, sorry.
So congratulations. It's wonderful you won this award. Yeah.
So congratulations, Nidhi. Yeah. Okay, next, the same John Paul Clay Award, but this time for a BA in biochemistry, is going to Fadel. I used to call him almost for a semester Fidel. I know that now it's Fadel.
Congratulations.
Congratulations on your achievement. Okay, now we are moving to another category. Basically, the student citizen, a student which participates in everything, and he or she was doing absolutely great. And she's helping people around her, and it's part of the life of the department. And this year is going to Ashley. Yeah, okay, yeah.
Congratulations.
Ashley, congratulations. Okay, next category. We recognize also the teaching, because we have a lot of adjuncts, we recognize the teaching in adjuncts, which are basically give us a new perspective. And the next award is going, and that it's embodying, it's calling Brighton Downey Award, or Downey Award, and it's in the memory of an adjunct from Hunter College. And basically, first is going to Olga Martinyuk. She's our former student. You know when you are old. Congratulations, Olga. Congratulations. So, you know when you are old, your students start to become getting awards, yeah? So, she was my student. Yeah, so, the same Barney Award, Downey Award, is going to Dr. Kundu. Yes. Congratulations. Okay. Congratulations. Okay, we have one more in the category of Downey Award, and this is going to our Habib. Hey, Habib. Hey, Habib. Oh, no. All, yeah. This is. Okay. Sorry, my bad. Yes, I tried to put it in order. Thank you very much. Okay. Now, we cannot close the evening without awarding, basically, is Arthur Sweeny Lecture Award. And basically, this is for an outstanding potential high GPA undergraduate research and service. So basically, it's embolding everything what is in Professor Sweeny. And this year, this is going to Andrea! Andrea, congratulations. Okay, and that is almost concluding. Yeah? Okay, no, that's okay. So that is almost concluding everything, but I would like, we finish this part, and I would like to invite Dean Mills to come to help me with another part of the ceremony. We basically, no, don't go. Where is moving? Alone. Okay, we are going to give the Latin honors. Yes, so basically, let me, come on. It takes two people to court. Yeah, exactly. So, first, Needy, summa cum laude. Summa cum laude. Yes, 3.85 and above. Yes, total GPA. Fadel. Yes, also summa. And now we are moving to cum laude. And that, Lashan, it's here, Lashan? Lashan, yeah, she's here. Lashan. Ashley. Jose. And Edward is here. Edward Solis is here. Edward, no. So we'll provide him later on, yes? So, thank you. And almost this concludes everything. Thank you very much, Professor Brus, for everything. I'll have few more remarks. So, before finishing, I want to think of three things, yes, especially to alums. Did you like what you see it here? Maybe. Do you find yourself, the little you, inside of the students today? If yes, please go to give to the Department of Chemistry whenever you have time and a little bit of something, yes? And you can make a little donation to us, yes? So, thank you very much for your attention, and you are invited downstairs for the dinner, for those which register. Thank you very much.